In the last part of this lecture, we will discuss a special condition. In the previous page, the two functions in the integral both have a uniform expression from t equals 0. In this page, f1t can be written as epsilon t minus epsilon t minus 1. f2t can be written as e to the power of minus t times epsilon t. You can find the value of f1t is 1 when t is from 0 to 1 and is 0 when t is greater than 1. At different time periods, the function's value in the integral is different. This means we should think carefully about the integral. We have two methods. In the first method, the expression of f1t and f2t on the total time axis are taken into the convolution integral for direct solution. RT equals the integral of epsilon tau minus epsilon tau minus 1 times e to the power of minus t minus tau times epsilon t minus tau d tau from 0 to t. You see, this is f1 tau and this is f2 t minus tau. Because this is an integral with respect to tau, so e to the power of minus t can be seen as a constant and taken outside of the integral. Then it times the integral of e tau times epsilon t minus tau d tau from 0 to t minus the integral of e tau times epsilon tau minus 1 times epsilon t minus tau d tau from 0 to t. Next, we will discuss the two items respectively. For the first item, we draw the graphs of epsilon tau firstly. Obviously, it's like this. Then we draw epsilon t minus tau. When t minus tau is greater than 0, its value is 1. In other words, when tau is less than t, the value is 1. So the graph is like this. The multiplication means only when the two functions' values are both 1, the integral has a meaning. By observation, we find the first definition domain is this, and the second definition domain is this. So the first item can be written as the integral of e to the power of tau d tau from 0 to t equals e to the power of t minus 1. Let's focus on the second item. What's epsilon tau minus 1? This is its graph. Its definition domain is tau is greater than 1. Epsilon t minus tau has been discussed above. It has value when tau is less than t. By combining them together, we know the integral has value when tau is greater than 1 and less than t. By comparing with the limits of the integral, we can find that the lower limit cannot start from 0. Because when tau is from 0 to 1, this expression's value is 0. So it can be written as the integral of e to the power of tau from 1 to t equals e to the power of t minus e. Next, we combine the two items together. The existence condition of the first item is that t is greater than tau and then greater than 0. The existence condition of the second item is that t is greater than tau and then greater than 1. So the result is divided into two parts. In the first part, 0 is less than t and less than 1. It only contains the left item. It equals e to the power of minus t times e to the power of t minus 1 equals 1 minus e to the power of minus t. In the second part, t is greater than 1. Now the left and the right items both exist, so it equals e to the power of minus t times e to the power of t minus 1 minus e to the power of t plus e equals e minus 1 times e to the power of minus t. You can find that this method requires the careful discrimination of the valid regions of different epsilon expressions. It's relatively complicated.